Let us start talking about Module 8. In this module, we're going to talk about Boolean algebra and Boolean function and their application in circuits. Our first lesson is on Boolean algebra and Boolean function introduction. Boolean algebra provides the operations and the rules for working with the set 0 and 1. Electronic and optical switches can be studied using this set and the rules of Boolean algebra. The three operations in Boolean algebra that we will use most are complementation, the Boolean sum, and the Boolean product. As a student, you can always associate these three operations to the logical operations of taking negation, disjunction or, and conjunction or and. As we will find out in the rest of this lesson, that the truth table using the two letter symbol 0 and 1 follows exactly same truth table as of negation in logic, disjunction in logic, and conjunction in logic. The complement of an element denoted with a bar is denoted by 0 bar equal to 1 and 1 bar equal to 0. So if I assume 0 is false and 1 is truth, then false negation is truth and truth's negation is false. The Boolean sum denoted by plus or by or has the following values. Remember, true or true is true, true or false is true, false or true is true, false or false is false. Similarly, the Boolean sum operates 1 plus 1 is 1, 1 plus 0 is 1, 0 plus 1 is 1, and 0 plus 0 is 0. The Boolean product or AND will have the following values. 1 dot 1 is 1, and if I want to see the logic version of it, then true and true is true, true and false is false, so 1 dot 0 is 0, 0 dot 1 is 0, so false and truth is false, and finally false and false is false, so 0 dot 0 is 0. When there is no danger of confusion, the symbol dot can be deleted and simply concatenation of 0 and 1 will be thought as the dot operation, the Boolean product. So using this notion, we're going to first see an example of finding the value of the Boolean expression 1 Boolean dot 0, Boolean sum, the complement of the Boolean sum 0 and 1. So as we have already seen, if I add 0 and 1, if I do that first and I do 0 and 1 using the Boolean sum, I must get 1. So putting a complement on top of it will get me the complement of 1, which is 0. Then if I do 1 dot 0, I must get 0. And finally, if I do 0 plus 0, I should get a 0, which is the result that we got in the example 1. So let's try to understand what is a Boolean expression and what is a Boolean function in the generalized fashion. Let B be the set of the two identity elements 0 and 1. Then B to the power n, which we will read as Bn, is the set of an n tuple x1, x2 up to xn such that each of these xi's are entries in the set B. So all these ordered elements x1, x2 up to xn are coming from your set 0 and 1. So they're either 0 or 1. This set is the set of all possible n tuples of zeros and ones. The variable x is called a Boolean variable if it is assuming values only from the set B. So anytime we use a Boolean variable for the rest of our discussion in module 8, the Boolean variable is either going to take the value 0 or 1, otherwise by definition it is not going to be a Boolean variable. The function Bn to B is called a Boolean function of degree n. And in very vague and easier sense to understand what is a Boolean function, you can think of defining a function from Bn to B that is simply using the algebraic expressions with complementation on the Boolean field. For example, if I use the Boolean sum, the Boolean product, and the Boolean complementation on the elements of Bn on the Boolean variables repeatedly, but for finitely many times, the end expression in terms of these variables is called a Boolean function. So we'll see concrete examples of Boolean expression and Boolean function, and that is going to make our understanding of these two concepts much more easier. In example 4, we are talking about a Boolean function fxy defined by x, y complement from the set of ordered pairs of Boolean variables 0, 1. And this is called a Boolean function of degree 2. And then we have found out if both x and y's are 1, then the Boolean function takes the value 0. If x is 1, y is 0, then the Boolean function takes the value of 1. If x is 0 and y is 1, then the value of the Boolean function is 0. If both x and y are zeros, then the Boolean function takes the value of 0. And it is simply understood and observed from the table on the left, where I have the xy column. Just like in logic, I have populated those two columns with the possible truth values of x and y. And even though I'm saying truth values, you can always say that truth is 1 and false is 0. And then you execute the function operation the way it is defined and described in the previous 2 pages. So once we have understand this thing, we can actually go ahead and start working on our problems and get the truth values to understand a function in its closed form. One last thing I would like to discuss is identities in Boolean algebra. And again, these are precisely the identities that we have seen in mathematical logic in our module 2 study. So instead of going over this discussion and example 8, I will go to the list of the identities and remind you those in the context of Boolean algebra. The law of double complement is if you take the complement of a variable repeatedly twice, then you get back the variable. If you add 2 variables, you get the same variable back. If you multiply 2 variables, you get the same variable back. It is called the idempotent law. The laws of identity, if I add 0 to any variable, then I get back the variable. If I multiply any variable with 1, I get back the variable. The domination law says that any variable added with 1 is always going to give you 1, and any variable multiplied with 0 is always going to give you back 0. The commutative laws are similar. It's 2 variables. When I am adding them, their order of appearance doesn't impact the result often. So x plus y is equal to y plus x and xy equal to yx. Associativity is x plus y plus z is equal to x plus y plus z. X times yz is equal to xy times z. The Boolean sum and the Boolean product both distributes over the other. So x plus yz is x plus y times x plus z, whereas x times y plus z is x times y plus x times z. Again, if it makes sense and helps you understand these concepts a little better, just replace all the pluses by or and all the products by and use your logical senses. The complementation of a product is going to be the sum of the individual complements. The complement of a sum is going to be the product of the individual complement. And as usual, this is your De Morgan's law. Law of absorption says x plus xy is always x, and x times x plus y is always x. The unit property tells us when the complement of a variable is added with the variable, I must get 1, whereas when the complement of a variable is multiplied with the variable, I must get a 0, and that's called the 0 property.